Mr. McBrien. This is SCH4U, Hess's Law. When we talk about energetics, we've already discussed some of the importance. But when it comes to looking at individual reactions and the energetics involved, maybe this example will provide some motivation and some context for why such things are so important. So in 2007 in Jacksonville, Florida, T2 Laboratories was doing a reaction to generate a compound called MCMT that's essentially an octane booster for gasoline. The reaction went out of control, and the resulting explosion sent debris more than a quarter mile from the factory, which was completely destroyed. 4 people on site were dead, 28 people on site and in the surrounding area were injured. Now, this destruction was caused by the fact that this reaction was insufficiently contained by a reaction vessel with a 15 centimeter steel wall. This is a picture of it here, or at least one of the pieces that was sent sailing through the air. So why did this occur? Well, the ensuing investigation assigned a cause of thermal runaway due to an inadequate recognition of heat and pressure generated in the reaction. In other words, the chemical engineers involved didn't understand the reaction that they were setting up. Okay, so unsurprisingly then, the Ontario curriculum would like us to be able to solve problems associated with these kinds of energy changes in a chemical reaction. And Hess's Law is one of the key tools that we will use to understand given reactions. So it isn't just about MCMT reactions and whether thermal runaway will occur. We need to understand whether a reaction will occur at all, how much energy we might have to put in because energy equals money, and our T2 Laboratories context of how much energy will be produced by our reaction and could this result in an explosion. Now we've learned how to use bond energies to get an estimate of the energetics involved in a reaction. But this isn't the only solution to the problem. This isn't the only way to attack this problem. Sometimes our reactions don't have bonds at all. Sometimes we have bonds that haven't been characterized. They just aren't in a table of bond energies. And sometimes, like in our cyclopropane case, extrapolation just doesn't work. So we can't use generic bond energies to understand the energetics of a reaction that we're doing today. So the question is, what do we do? What do we do in these kinds of situations? Well, the answer is to take a step back. So what we need to do is reassess our situation. So in order to do this, I'm going to form a metaphor, and hopefully this will help you to understand very well how Hess's Law can apply. So let's consider the question of elevation. Let's imagine that we have the problem of wanting to know the elevation change between a location we're at today, let's say in Burlington, and let's say that we want to understand the elevation change to, for example, the summit at Kelso. So we could potentially measure that change in elevation explicitly. We could go and do the trip, use a GPS, and figure out the change in elevation. But is there an easier way to do it? Well, the answer is that if we have a reference and we know the difference between us and the reference and the difference between Kelso and the reference, then it becomes a trivial exercise to calculate the difference. And in fact, we have this. So if we know that the elevation change for our location to a known elevation level, let's say Lake Ontario, if we know that that's 32 meters difference, and if we know that the elevation change between Kelso and Lake Ontario is 307 meters, well then we have our answer pretty easily. So all we have to do in that case is just simply subtract, and our elevation change between here and Kelso then would be 275 meters. So this is exactly what Hess's law does. It essentially takes that same idea and one simple assumption that reaction energetics are independent of the path taken to get the molecules. And what that means is we can take and we can say, if we need to know the energetics for a target equation A to C, but if we know the energetics to get from A to B and from B to C, then we can apply the first law of thermodynamics, say that energy has to be conserved, it can't be created or destroyed, and we can just simply do the math. So this basis for calculating enthalpies of reaction is known as Hess's law. And what it states is that the overall enthalpy change in a reaction is equal to the sum of the enthalpy changes for the individual steps in any process. And anytime you can write an energy difference between reactions and reactants and products in any route we want, then the energetics will be independent of that route. So we can state the equation then in this kind of form, if, of course, the animation will work. So the overall then Hess's law equation would be that the enthalpy change for a target equation is equal to the sum of the enthalpy changes of a set of known equations that will give the same, that will sum to the same result. Or the enthalpy change of the target is equal to the enthalpy change of reaction 1 plus the enthalpy change of reaction 2, etc., etc. Okay, and there's only a few rules we need to keep in mind. First off, if in order to get the reaction we need, we have to reverse a known reaction, well then we have to change the sign. So if it was a negative heat of reaction, we need to make it a positive. If it was positive, we need to make it negative. If the coefficients of the equation need to be altered, for example, multiplying or dividing a reaction by a constant factor to get what we need, well then we also have to multiply or divide the energetics, the value of delta H. So it's probably easiest for us to take a couple of examples. So let's say that we wanted to know the energetics of the oxidation of carbon, but we had only the energetics of oxidation of carbon to carbon monoxide and oxidation of carbon monoxide to CO2. In other words, the only, in this case, the only reference equations we have are the two-step path to get to carbon dioxide. If we have this situation, it's a trivial exercise for us to simply look at this, sum the overall reactions, so adding together all of the reagents and all the products, and when we do this, sum the energetics as well. And then there's only one step we have left. We have to recognize that carbon monoxide is on the right and on the left, and that we can cancel it. So we cancel this, We cancel this, this reagent that's on both sides, and then we're left with the reaction. We're left with the reaction that is our target. So we've used two steps to get the energetics for a single step reaction. So let's take a more complicated example then. If we have a situation where we want the enthalpy change for the formation of 2 moles of nitrogen monoxide from its elements, we can first write our target equation. So nitrogen plus oxygen to give nitrogen monoxide. And notice that we've got 2 moles here. Let's imagine that we're given 2 reference equations and asked to create this overall expression. So this is a very common test question. Given these 2 expressions, state the energetics for the target equation. So we can call these the known equations and call the other one the target equation. Now our challenge becomes to manipulate these 2 equations, then be able to add them together to get the chemical equation for the formation of 2 moles of nitrogen monoxide. So if we look at this equation first, this will give us a context for what we need. Our target expression needs 1 mole of nitrogen. Our known expression only has half a mole of nitrogen. So how would we modify this in order to get it to 1 mole of nitrogen? Well, it's pretty simple. We multiply it by 2. Now, if we're going to multiply that equation by 2, we also have to multiply the energetics, the enthalpy, by 2. And so the net result is 2 times a half is 1 mole of nitrogen, 2 moles of oxygen, 2 moles of nitrogen dioxide, and 68 kilojoules. So if we do this operation then for the first equation, that's fine. The second equation, as it turns out, needs to be reversed and then multiplied by 2. And so we do that as well. Once we're finished, we have these 2 expressions. We can add these together, and this doesn't look anything like our target equation, unfortunately. Well, in fact, that's not such a big deal. The reason why, we need to recognize that we can in fact cancel the nitrogen dioxides, which aren't part of our target expression. And then we need to recognize that oxygen is on both sides of the equation as well. Well, in this case, we have 1 mole of oxygen that can be taken care of here, and this gets rid of the 2 in front of oxygen on the left-hand side. And when we're finished, there we go. We've got nitrogen plus oxygen to get 2 moles of nitrogen monoxide. And in fact, we can just add together this energetics here. So 2 times 34 plus 2 times 56 gives us 180 kilojoules. So our overall expression then is achieved, and we can find that our enthalpy involved with the production of 2 moles of nitrogen monoxide, we will have to put in 180 kilojoules of energy in order to achieve the reaction. So the big challenge with these kinds of problems is really just determining how to manipulate the known equations to get the target equation. Okay, there is a second kind of problem like this, and really this is no different than the expressions we just saw, except we need to realize that in some cases we won't be given the equations we need to produce our target equation. Instead, we need to remember that concept of heats of formation. So remember that the heat of formation is the heat required or produced when a mole of a given compound is created from its component elements. For example, if we want to make a mole of liquid water, we react hydrogen with a half a mole of oxygen, and the heat of formation is negative 286 kilojoules per mole. Now, why is this useful? Well, these heats of formation have been carefully characterized for many, many compounds. And what this means is it gives us known equations that we can manipulate in order to generate target equations. So all we have to do is use the heats of formation for any element that is not in its standard state. So, when we know the heats of formation of our reactants and products, we can then use these to generate the energetics of the conversion. So let's take an example to illustrate this. So let's say on a test we're asked, calculate the enthalpy of reaction for the combustion of nitrogen monoxide gas to form nitrogen dioxide. And here's our target equation here. So when we have this kind of situation, I'd encourage you to take this approach. Look at the expression and see what reactants and products are not in elemental form. So you can see that oxygen here is in elemental form. We don't need to worry about this, interestingly enough. What we need to do is focus on this reactant, which is not in elemental form, and this product, which is not. These are the ones where we have to go and look up the enthalpies of formation. So we go and look those up, and we write the expressions for them. So guess what? Here they are. Here's the enthalpy of formation of nitrogen monoxide. Okay. And here is the enthalpy of formation of nitrogen dioxide, our product. Now what we have to do is we want to reverse the one for the reactant and leave this one alone. So our reactant, remember, okay, so here's our target equation. And we have to go and combine our heats of formation reactions to create our unknown. So here's our desired reaction. We reverse the one for the reactant, as I mentioned, and of course we reverse its sign as well. So this gives us, and of course this is no longer the heat of formation. This is just the enthalpy for the reaction as written. Notice now we've got our reactant is in the right form. Now the other equation was already in the right form for us because we have the product on the right hand side. And then we can add these reactions together. Recognize that nitrogen is on both sides and cancel it out. Recognize that there's half an oxygen on the right hand side, and so with a whole oxygen on the left hand side we'll introduce the 1/2 modifier. So we're essentially subtracting 1/2 mole of oxygen from both sides. Then we can add these together, and guess what? We get our target equation. Once we do this, of course, then we can add the enthalpies together as well. And we can see that this is an exothermic reaction, reacting as requested nitrogen monoxide with oxygen to form nitrogen dioxide. And this is the enthalpy for the reaction involved. In fact, in many ways, the heats of formation approach is the easiest way to apply Hess's law. Okay, so to sum up then, Hess's law is simply a restating of the first law of thermodynamics. The energetics of a reaction is determined by the sum of the energetics of any set of reactions that can sum to the target reaction. In order to achieve what we need, we can manipulate given reactions algebraically, including effectively multiplying by -1, reversing the direction of the reaction. And we do this in order to match the stoichiometry of the target reaction. As soon as we have sets of equations that we can sum to the required equation, then we can use the energetics involved. We have to be careful when we manipulate equations algebraically to get a given reaction. We have to apply that modifier to the energetics term, to the enthalpy as well. Now, these heats of formation that we talked about yesterday are very interesting for use with Hess's law because they're well characterized and because they're pretty easy to manipulate. Okay, so for today then, I'd like you to work through the Hess's law worksheet and be sure and read over the note for today as well. If you're curious about the T2 Laboratories example that I cited today, there's a pretty good summary of it online in the first chapter to this book. So feel free to have a look. Thanks very much and have a great night.